Good afternoon. Welcome to today's SCA webinar with Dr. Everton Arujo of Subsurface Alliance. He'll be speaking on the geomechanics of CCS, why, how, and when. Before we start today's webinar, I'd like to ask a few questions about the demographics of the audience. So I'm going to launch a poll, and the first polling question is, what is your primary discipline? So we're starting to get some responses now. Looks like we have quite a few petroleum engineers and geoscientists in the audience. So roughly 2/3 geoscientists, 1/3 petroleum engineers, a few petrophysicists, a few other. And I'll go ahead and close this poll and share the results. We have 63% geoscience, 26% petroleum engineering, 4% petrophysics, and 7% other. So let me go to our next polling question. How many years of full-time experience do you have in the upstream oil and gas industry? We are getting responses now. Looks like we have some in every category. Most of you have voted, so I'll go ahead and share the results. It looks like we have 13% with less than 1 year, 19% 1 to 10 years, 35% 11 to 20 years, 23% with 21 to 30 years, and 10% with over 30 years of experience. So thanks for that. I will go ahead and share my slides. And again, this is, the talk today is Geomechanics of CCS, why, how, and where, and when. And Dr. Arujo is managing partner of Subsurface Alliance. He has more than 20 years of experience in working as an expert in geomechanics with projects around the world. He has 3 degrees in civil engineering, including a PhD, master's and bachelor's, all from universities in Brazil. And Dr. Arujo teaches a class for SCA entitled The Geomechanics Aspects of CCS Projects. This course is available in-house, taught as a private in-house course. So please contact us if you're interested in having this at your place of work. We have free webinars upcoming in December. We have Dr. Birol Dindaruk and Dr. Sylvia Levescu will be speaking on geothermal energy. That's a month away, Thursday, December 7th. And looking ahead, we're about to launch our advertising for our calendar for next year of training classes. And one of the highlights is Dr. John Lee. He will be teaching 2 classes in live online format. The first class is production forecasting for low perm reservoirs, and the second class is PRMS and SEC reserves and resource regulation. Both of those are offered in March. And of course, we can have private in-house classes at your location. You can attend one of our public courses, and sometimes our classes are offered in live online format. And of course, we have field trips. And in addition to training, SCA is well known for our consulting expertise, and we also provide staffing services, and we can conduct projects and studies for you. So I'm going to give the presentation rights back to Everton. And I will remind the audience that you are muted, so if you need to ask any questions, please put them in the question feature of GoToWebinar, and we will ask them at the end of the presentation. Over to you, Everton.
Thank you, Susan. Thank you, SCA, also for the opportunity of one more time being here and talking about this very popular subject of these days of carbon capture and sequestration, in our cases related to the aspects of geomechanics. And today, that's what we're going to cover. So the title of the presentation says for itself, Geomechanics of CCS. But then we kind of try to address why, the how, and also when we should do geomechanics related to CCS. On this first slide, I would like to bring up some sort of two pictures that kind of gives the idea of how geomechanics has been evolving over time since it has been introduced over like 30 years ago inside of the oil and gas industry. In this right side plot, and let me get my pointer. On this right left side plot, we see two database data that we did a quick search on what papers have the title, in the title, the word geomechanics. So we look at the one Petro database, which is the one that SPE and all the technical societies organize, and it collects a lot of trade shows and conferences, presentations by technical work, and also the Science Direct by Elsevier, which is pretty much the scientific journals that involve these many disciplines, including geomechanics and geoscience and engineering. So basically, we go there and we type and look for a paper that has the geomechanics in the title. And this is on the vertical axis, you see the number of publications. In the horizontal axis, you see the timeline. So you see that by the early 90s, we got something very minimal. If someone was really talking about geomechanics, it would be something like everybody probably would say, what is that? And as the time goes by, and then we kind of start hitting the 2000, by the moment we switch the century, geomechanics was getting a little bit more popular. And by 2010, we start getting something around 50 plus publications in those two databases. And as you can see, the growth has been exponential all the way to the present day. So right now we can kind of get like 250-ish publications by these two databases with papers that comes with the geomechanics in the title, something related to geomechanics. And one thing that you can really see over the last 3 years, from 2020 to 2022, during the pandemic, right, that most of us were confined and we could not really go to conferences. You see that the drop in the green bars, which is pretty much the one Petro by SPE, which is you have to present a paper in a conference so it can be listed in that database. But since there were basically no conference and some conferences were only virtual, there was a significant drop during the pandemic. However, the interest in the number of people working on geomechanics did not change at all. Since people could not go to conference, they basically switched the gears and start publishing in scientific journals. You see that the big increase in the red bars over the last 3 years. So in other words, the geomechanics discipline has been getting consolidated inside of the energy and mostly the subsurface related energy matters in oil and gas, and in these days in the storage of hydrogen, in these days also for the carbon sequestration. On the right side here, we kind of try to break down, okay, there are geomechanics and geomechanics applications, right? So we try to classify in 4 different major categories here, and then we say that, yeah, wellbore geomechanics still dominates the party. It's pretty much everything related to drilling, completion, stimulation, and production of the wells, right? So there are a lot of geomechanical applications in these matters, like pore pressure prediction, wellbore stability for drilling, sand production prediction for casing and completion selection, hydraulic fracture for stimulation, and also production related things that goes into that major group. Second, it comes reservoir geomechanics. What is pretty much these days these 3D models that as we have very powerful computers right now, it is very much easier than it was like 10 years, 15, or maybe 20 years ago when I started. Running 3D models was not a thing for geomechanics. It was basically impossible. You would put a model to run, it would take like 4 weeks to get that realization back, and sometimes it was impracticable. So you couldn't do it. So right now, because of the power that we have in computational capacity, we can really go and start doing these 3D models. Geohazards have become something of common these days too, and pretty much when it comes to geohazard, here we're talking about induced seismicity. because of the huge amount of unconventional wells drilled, fractured, and also the wastewater that we have to dispose from those wells. There's a lot of seismicity, and I'm sure everybody have heard about the earthquakes in places that pretty much were very quiet before, like the West Texas, but because of the huge activity that we have right now there, injecting and disposing a lot of volume of wastewater, we are creating induced earthquakes, right? And late, something related to what we're going to talk today, the energy transition, or some people call energy addition, but this is talking about if we can store carbon dioxide or hydrogen down there in the subsurface and keep them as a place to store and then maybe later utilize it or permanently sequester that fluid over there. So you can see that there is already kind of a number of publications coming to that point. And for some people, geomechanics is still not really well defined, right? So we have put together a nice kind of a blog type of article here. Geomechanics, is that a geoscience or engineering? So if anybody is curious and want to take a quick read, that's a good one to have. So some companies classify geomechanics for more like an engineering type of a discipline. Some companies more like a geoscience. In reality, geomechanics is an integrator. It sits right in between geoscience and engineering, and really kind of talk both languages and making that bridge to connect both worlds. So now more specifically, when it comes to the carbon capture and sequestration, where geomechanics really sits. There are three major pillars for carbon sequestration in the subsurface, and basically the first one is the capacity, where most people are talking about these days, because before you really consider doing any of these operations, we have to find out that if you do have the volume available to inject the CO2 in the subsurface. And that pretty much comes to the thickness, the structure, the extension, and also the porosity, right? You need to find out the pore volume. At that moment, geomechanics has no role. So that's not where geomechanics gets any kind of a role in that negotiation here for the project. But as we move to the second pillar, which is injectivity, then things that are going to be impacted by geomechanics are going to be right on the spot. Like the permeability, for example, if the rocks are naturally fractured, those fractures are going to reactivate and open up quick and faster channels for the plume and the fluid to migrate. That's one thing. Or if those fractures are going to be stress dependent, depending on the pressure, they may open or they close. The fluid pressure is going to be one thing that we're going to have to deal anyway, because that is going to change the original pressure in the receiving, the intaking formation, right? So either depleted or non-depleted. And that is going to be quite correlated with the fracture pressure that we're going to ask this question. How much the rocks can tolerate pressure before they really crack? And that goes pretty much back to the well operability, because that's the intake point where most of this pressure and the majority of the disturbance is going to occur. So the well bore is going to be probably the weakest point and things around that. And then how the plume is going to extend and CO2 streams, all are going to be somehow affected by geomechanics. But really, when geomechanics really takes probably the driver's seat, is when it comes to the containment. The ultimate goal of the sequestration of carbon dioxide in the subsurface is to permanently keep that fluid down there. So we need to make sure that we have the integrity of the system, mechanical integrity. We cannot allow for the fluids somehow find a way to escape, migrating out of that place, going to places that we don't want them to go. So there is no point for injecting the fluid and let that fluid escape later on. So then we have to worry about the seal or cap rock integrity, fault stability, because they may become the easiest path for fluid migration if they get reactivated or slip. Natural fractures, they're going to be somehow connected to faults. And if the volume that we estimate is not that great or big enough to take all the volume that you're going to take, this reservoir is going to inflate. That inflation likely may be propagated all the way up to the surface. And if that happens, you may affect some structures nearby, or you can get a very clear cut that something is going beyond what you expected in subsurface. If you are seeing deformation at the ground level, in other words, that means that something is going down there that probably beyond the limits that we anticipated. So seismicity is going to be related to fault stability. If there are faults and they reactivate, seismicity is going to be created. Well integrity, and also we can tie this all back geomechanics with monitoring techniques, and we're going to show some of these cases along this presentation. So to the right side here, we have a few of these containment issues that we may be affected by doing CCS in the subsurface. If you come with a well and you start bringing a pressure, a fluid that comes with pressure and temperature that are different from the intake information. So we're going to create two type of fronts. We're going to creating a cooling and a pressure front that's going to go from the well all the way across the reservoir, and that is going to create a few disturbances in the system, the mechanical system, that has to be addressed before you really go and say, oh, we are safe, there are no risks, and we can keep injecting X amount of tons and nothing's going to happen. So things that we have to be worried about, for example, are we going to maintain the seal integrity? Is that possible that for a certain condition we may achieve the frac pressure in that seal? And if that happens, and eventually if you have natural fractures, can them connect to each other and propagate that kind of pathway for fluid migration? Or when we also have faults to a lesser or to a greater degree, are the faults going to be affected by this pressure and cooling front? And if they're going to be affected, how much are they going to reactivate? And if they do reactivate, there is a chance that now there is an easier way for fluids migrating here from the reservoir upwards, maybe to fresh water horizons, or eventually escaping up to the surface. So these are a few things that we're going to have to worry about. And then in terms of the risk, when we look at the left side picture, you see that as the injection begins, the risk starts to increase, because as much as we can do to characterize, collect data, there will be always uncertainties. Subsurface, we deal with uncertainties, right? And as we start doing the operations, the injection, and we may start kind of a testing, we will test this system, and that test is going to put us against the models that we put together. And if everything goes against the model, we're going to see breaking here, breaking there, and that's the moment that the models need some updates and recalibration. So the risk profile is going to keep growing all the way up to the end of the injection, right? Because more volume is getting there, you're pushing the system harder and harder. By the time your first injection period ends and things start moving more to, okay, I have a lot of data, nothing happened, or something happened and I recalibrated the model. So the risk should decrease as a secondary, a tertiary, or whatever many new cycles may come along that injection. So anyway, your injection is going to grow as you start doing the operation, and the geomechanics model has to be kind of working on the same way we do history match for reservoir simulation. History match and we do forecast. And then as the new data comes in, we recalibrate that model and keep improving the forecast and the predictions. Some people may ask, okay, what is this geomechanical model? It's nothing more than really a mechanical, mathematical description of the subsurface elements that drives and defines how the rocks are going to deform and eventually crack when we submit them to an external loading, right? External pressure that we're bringing in, an external temperature that we're bringing in. And those things created a disturbance to the system that was once before in equilibrium. And if you push too hard, they're going to reach a limit. All the materials can break at a certain point, and rocks go the same way. So in other words, we need to constrain the input data for the models that we run. And in other words, we need to get a control of vertical stress, the minimum horizontal stress, the maximum horizontal stress magnitude and azimuth, the mechanical rock properties, and the pore pressure. So a geomechanics specialist, he will go and they will build a profile over depth for every single of these elements, because with those elements, he can be able to input this into a sophisticated model and, let's say, for example, calculate if X amount of PSI excess of pressure is going to create a scenario that the fault may be slipping and creating a reactivation scenario. But life is not that easy for geomechanics, right? Because the geology is not really uniform across all the places in the world. We have different stress regimens depending on the tectonic activity of the place. And by the Andersonian classification of what kind of a faulting regimen we have at every single location, basically they have these three major types of faulting system occurring or that have been occurring in the past. So when we have the vertical stress, the SV here, as the greatest stress at that moment in that location, we are under normal fault. So we know that sigma 1, as we call in geomechanics, is going to be equal to sigma V or SV. And both horizontal stresses are going to be lower than that. However, some places are into strike slip when you have a more lateral push that is going to be greater than your vertical stress. So you're going to be a strike slip condition. And if you are in a more, let's say, not so favorable scenario, in a reverse faulting, your minimum stress at that location can be overburden. And all these three scenarios, depending on the arrangement of the magnitude of these three stresses, may put the system more or less at risk of failure. And that's part of the game all the time. The geomechanics analyst or specialist is going to constrain these stresses, and he's going to use these stresses to determine if the faults are going to be stable, what kind of pressures can break the cap rock, and things like that. In a nutshell, in terms of graphical description in numerical fashion way here, you can have over depth a representation profile of these elements that I just mentioned in the previous slide. So for example, here in this case, we have in the black line here, the vertical stress. And as you can see in this case, it's the greatest stress. So we are in a normal faulting stress regime in this case, as my maximum horizontal stress is lower than maximum stress, and the minimum stress is lower than the horizontal stress here, the maximum horizontal stress. So we get a normal faulting here. In this case, we would have some sort of overpressure that really a little bit below 2000 here departs from the hydrostatic gradient, and all those elements goes into geomechanical model. We also look at the indicators of stress orientation like calipers and whole image data to get breakouts or drill-induced fractures. So you can see here we got the stress orientation in this case more or less like north and south for the minimum stress, and the maximum stress would be here perpendicular to the breakouts orientation. And also we get also along the well path description of the mechanical properties. In this case, we have the internal friction angle and the UCS, pretty much telling that, for example, rocks at this level here, let's say if this is your cap rock, you have a 30 megapascal compressive strength, while the rocks underneath are much more at the 10 megapascal. There is a contrast in the strength here between the rocks on the cap and the rocks on the reservoir layer here. In terms of mechanical properties, when we deal with this characterization for oil and gas operation for regular oil and gas production, we take core and we measure that in the lab for mechanical and physical properties like fluid flow, right? For geomechanics, we take it to a loading machine and we load those samples all the way for the failure. We really crack the rock because we are interested to understand how much the rocks will deform here. You see the strain against the stresses that we apply. Let's say as we increase the stress, the rocks are going to be straining, and it's going to reach a point that they're going to break down. They're not going to be able to take any more mechanical loading. They break down. But when it comes to the CCS, we're going to have an additional type of problem because the CO2 is going to create in subsurface an acidic environment, and that acid is going to create some sort of a dissolution of minerals in the cementation of the rocks, weakening the material and creating a material that's going to be easier to deform and also easier to break down. You can see here a contrast between the red and the black being the intact rock, the one that was not exposed to CCS or CO2. And the red one is after some time of exposure. You can really see that there is a drop in the strength, and that's for a sandstone. That usually is a rock that's not too reactive. But for people considering doing CCS in carbonates that are very sensitive to acid dissolution, so you can really see that these impacts can be significant here. You can see here on the blue curve intact rock that has not been exposed to CO2, but after the same or similar rock has been exposed, you can see a significant drop in strength. You can see the maximum peak stress here was around 17. Here was barely above 10. And also the deformation parameters in terms of Young's module. This Young's module is going to be very important into the 3D models because it determines how much the rock deforms based on the loading that we're applying. So you can really see that there was a drop of almost a 40% in Young's module. In other words, my rock is going to deform 40% or 60% more when it's exposed to CO2 than if it wasn't. So that's quite a very important thing to consider. Also, you can see here in terms of the failure envelope, a significant drop. You can really see that the cohesion and the internal friction angle really decreased significantly after the exposure to CO2. So this is going to be very critical and very important because if by any chance we believe that, let's say my rock can take all the way to 15 to break down, actually after exposure to CO2 it can break down by 9, and that can compromise or change the design of the wells and some operations of the project. Or can even say, well, maybe you cannot go past this limit in pressure because if you stress the rock more than that, it's going to break down. So it can put a cap on the operation limits. In this picture, we are showing here a 3D model that uses the finite element method technique to really calculate the stress, strain, and eventually failure of the rocks. In this case, it's a particular one because it's for an offshore Gulf of Mexico field where we have the presence of a salt dome or diapir, if you call that way. And one particular thing on when we are thinking about doing operations near these geological features is because they're going to create additional changes in the geology and also the stresses around those features. So you can see here that the color map shows the magnitude in PSI of the maximal principal stress, let's say sigma 1. And you can see that there are locations with a high compression here in the red and someone not so much here in the purple. So in other words, let's say, for example, if you want to frack a rock here, you're going to take a harder time of doing that. But if you are fracking around here, you're going to be much easier. And also you can see that the vectors direction kind of a change away from the south body. The sigma 1 here tends to be vertical. In other words, it's your vertical stress. But as you approach to the salt structure, the salt mechanical behavior, like a creeping material, kind of makes those stress to rotate. And that creates an additional type of consideration that has to be taken into account here. So we cannot really make an assumption that a vertical stress is going to be principal 1 and go by that for the calculations, because we may be under predicting the scenarios near these complex structures. So if we are considering going to the offshore and near salt, we have to be extra careful here when it comes to these mechanical related aspects of the subsurface. Cap rock integrity is probably one of the major concerns about CCS. I think yesterday I was reading an article about one project that was denied the permits by the authorities in North Dakota. I just don't remember the name exactly here right now. And the main article that I saw on the web yesterday was that the authorities felt that the concerns about the facilities and the environmental issues and people around that project would be something that would not be okay at this moment. And the project was canceled, but the company applied for a reevaluation or reassessment or things like that. And the reason is because the population is going to get concerned, right? People that do not really understand subsurface, it's very natural that they're going to feel skeptical about, okay, you're bringing this amount of volume of carbon here to inject, and are you going to create things? Because right now, if people can really make a easy analogy is going to be to the unconventional wastewater disposal in the West Texas, right? They say, well, before that type of activity, Texas was quite was free of earthquakes, and now we are getting up to 5 degrees magnitude. So the population, communities, politicians, regulators, they're going to be watching for this type of thing. And until there's a lot of studies done and really proving that this can be done in a safe and an effective way, there will be some hurdle. Like this project of yesterday, it was just not granted the permit to go ahead because of the concerns for the population and environment around those site locations. And I'm highlighting here 2 types of studies that have been done in the past, 2014, 2020, trying to address this type of a concern. Really, researchers and consultants really going and picking some cases to really do some assessment to see, okay, these are the risks, and this is what can be done to educate and get the support of the local population and the authorities, the local authorities, for the permits of this type of a project. And this is all related to geomechanics. Now getting a little bit more into the nitty-gritty here about, okay, pressure and temperature, right? So I'm bringing up an example here of the Gulf of Mexico, for example, geothermal gradients. If we break down the Gulf of Mexico region in 3 major ones, Western, Eastern, and Central, we can get this type of profile. A supercritical CO2 temperature is going to be around 31 Celsius degree. You can really see that there is already a difference between temperature. The CO2 is going to be colder. And as deeper as you go, that difference is going to increase even more. And this is quite important because when we cool down the rocks in subsurface, we're going to create something called thermal stress. This is not the thermal stress that exploration people talk about in terms of maturation. This is a thermal stress, like, let's say, when you are cooking and you have your cooking pan on the oven, and then that metal is expanding because you are heating up, and that material is going to increase volume. If you heat up the material, the volume is going to increase, but if you cool it down, the volume is going to shrink down. And that's what happened with the rocks in subsurface. If you have, let's say, for example, original temperature at this value, and as you inject over time, you cool down the reservoir and the interfaces of the cap rock, and actually that cooling effect can go into the cap rock, even though there is no fluid flow into the cap. The rocks are going to feel like, okay, I need to shrink down, and that shrink is going to drop the stresses. Like if my original stress value was at this value, now I can have some sort of a drop here. Doing a quick math for regular parameters in terms of geomechanics, you can get like a 400 psi-ish stress reduction by just using regular average parameters of thermal expansion and Young's marginal Poisson ratio for the rocks. That 400 psi can put you at the risk or eventually a no-go for any project that's really close to the border. This type of study has been done in this case here for this Ohio River Valley feasibility study. They have a lot of coal plants in that location. They say that's a good location for injection of the CO2 because the producers of that fluid is right here, so we can kind of inject in this location. So the specialists for these studies here, they did the classification, and then you can see here in terms of the geomechanical model, they have the maximum horizontal stress as the greatest one. In other words, they are in a strike slip condition. The vertical stress is in the intermediate, and the minimum horizontal stress is the least one. Pore pressure kind of follows a hydrostatic profile here. So, and they were concerned about this thermal stress effect. In this plot, that's what they kind of really kind of trying to figure out. So there's a lot of curves here, and I'm trying to give some explanation of the 2 different scenarios. The equation for the risk calculation is what the shear failure risk, which is pretty much the differential stresses that are being created in the subsurface compared with the rock strength parameters in terms of friction angle and cohesion. So when this value is greater than 1, you are creating a shear fracture in the rock. When it's less than 1, you are not creating that. So then they evaluated this scenario. That equation here is plotted as a stress level here on the right hand side vertical axis. And they kind of compare 2 scenarios: isothermal, not considering temperature, and when they activate the thermal effect. So they can really see here that if there is no change in temperature, your stress level here, it really stays below 0.55. In other words, you are not really approaching the risk of fracking the rock. But if they activate the thermal stress, you see the difference in the orange curve here that starts increasing and really goes above 0.7. It's not really 1, but you can see that the risk significantly increases. And that's basically because you change the pressure and you change the stresses, and those two changes create an additional risk for the rock material. So in this case, it still was okay, no significant risk. However, you can see that you cannot really say I'm super safe and nothing is going to happen. So if by any chance, for example, they have to increase the pressure, the injection pressure even more, maybe eventually these numbers can go beyond 1. And that's why those numbers kind of really grow. In terms of graphical representation, we in geomechanics we use these things called the Mohr circles, right? In other words, it's really like we compare what are the maximum stresses with the minimum stresses, and then we do draw a circle around these two limits. And the failure envelope is given by the friction angle and the cohesion or unconfined compressive strength. In other words, if your Mohr circle is below the failure envelope, your rock is safe, it's not going to break down, it's not going to crack. When these Mohr circles, they pass the failure envelope is the moment that you are stressing the rock beyond the failure envelope, in other words, beyond the strength. So when we do a cooling effect in the rocks, you can see that we go from the blue scenario to the red scenario here, by just taking into account the difference in temperature in the subsurface and with the CO2 that is coming from a cooler scenario. But we are doing two things. We are doing a cooling effect, and we are also increasing the pressure. This delta P is the increasing pressure, right? So if that happens, then we can really put ourselves in that scenario of failure. And that's the moment that things may be a little bit off the limits for safety and operation efficiency. And if you really compare the stress level and the pressure level with, let's say, depth, because the deeper we go, the higher the stress is, right? And the deeper we go, the stiffer likely are going to be the rocks, so the greater is going to be the temperature impact. So we have the temperature on the left and pressure on the right, and on top we have the shallow horizons and deep horizons. And of course, the shallow and deep, these are going to be dictated by the stress regime in the location. If it's a strike slip, a normal faulting, or reverse one. But assuming that we are under a similar stress regime here for the shallow and the deep, so you can really see that when you are at the shallow horizons, the temperature effect cannot really be that significant. And the increasing pressure seems to be a little bit more pronounced. It can push you a little bit more close to the failure. However, if we are at a deep, and deep doesn't really mean that it's like a double a depth for the shallow, it can really comes to the limit that say, okay, now the stresses are great enough to push this Mohr circle beyond the envelope. You can really see that the temperature effect is going to be probably dominant. And here they are even comparing, for example, the green line here is for a fault. And again, the fault should be the first one to go and the break, because they have been broken down before. And you can have some fault reactivation and then fluid migration across the fault. So these are the things that have to be done in the geomechanical characterization for example, when you are permitting class 6 wells, you have to do this type of analysis. You have to prove to the EPA or any other regulator that you have considered all the scenarios that are possible, and maybe not so much probable, but are possible to happen, and you have looked at that. Because people may say, oh, this is not so common, this is not something that we see every single day. But it happens, and when it does happen, really creates a mess and really creates a showstop for the game. This is a case of an offshore field in Brazil, nothing related to CCS, but the physics is about the same. So there were injector wells in this field and producer wells, and by the time this blue well was being drilled, so parallel to the major fault in the field, that you can see that that major fault goes very close to the seabed. There was an incident, a drilling incident called a kick. The pressure in that formation at that depth was greater than the mud pressure. The formation fluid invaded the well, and for safety, the blowout prevent or BOP was closed. But that increasing pressure inside of the well was not something that the formations were able to contain. There was a crack that was created at the shoe, and that crack propagated and likely connected to that fault that could not handle that pressure, and eventually that fault propagated all the way. It was already very close and just propagated close, and next day showed up a very nice crack at the sea bottom, and you can really see the oil coming through that crack. And that's the fault line that comes all the way to surface, because the pressure was put to a level that the fault could not handle anymore. And this is the result of that migration of oil, a big sheen on the surface of the water. I don't need to say that this was a big problem for the company operating this field, and these things does happen. And if we do not take care and do not look at these things, they happen, and sometimes they get us by surprise. So now, going back to a more onshore situation, this is for the Insala CCS project in Algeria, probably one of the most studied projects in the world when it comes to many different related things to geomechanics. On the left side here, we're kind of comparing the curves are the pressures, the blue is the injection rate, and the red is the wellhead pressure, with the number of events in the black bars for the induced seismicity. You can see that as the pressure was going up, the number of events were okay to a certain point that they start increasing, and then when it came to more or less this level, the number of events really increased. You can really see a big jump in number of induced seismicity events, and if they cut down the pressure, those events start going down. In other words, fault reactivation is happening here, and it's really reflected on the pressure. On the top picture here is real data. On the bottom is simulated data. So you can really see that there is a good correlation between simulated and real data. So this is geomechanics simulation proving that yes, once we have data, we can calibrate and then use that for forecast. Another way to use geomechanics to monitor and see how things are going in subsurface is looking at the satellite image monitoring for the ground displacements over time. You can see here that this is on the top, we have a picture of the region. This was the well here that was getting these events after one fault that this well was crossing, reactivated, and you can see that around that well there is kind of a good heat map here that shows that there was about like a 15 to 20 millimeters displacement at the surface. That's not much, but tells you that something is inflating enough in the subsurface to create the ground level to go up. And the bottom picture here is the same, but completely modeled by geomechanics. You can really see that you can get a very good representation of what's going on down there and correlate that with the data. In other words, you can combine these monitoring techniques, satellite and microseismicity, to really see if you are coming close to the limits, safety limits, or if you have passed those limits. So very important and very accurate way of doing this over the time you are doing the operations for the field. In terms of offshore locations, the most active projects in this matter are the ones in the North Sea by Equinor, right? So in this case, they were concerned about, again, the thermal effects on the integrity of the cap rock. This is the Northern Lights project that have been quite studied at the moment. Cap rock is the orange, the intake formation is the Johansen, but the ultimate storage is the Cook, because CO2 is going to migrate upwards by density buoyancy, right? A difference. And they were concerned about that. Okay, we're going to be operating for 25 years injection in this fluid, so we're going to cool down this formation by 80 degrees Celsius. That's significant. And how much pressure this is going to create and change the system. So you can see that as we cool down, the wells here are on the left, as you inject, you start cooling down the reservoir, but you also cool down the cap shale. And because you're cooling down the shale, the pressure in the shale is dropping, and this is reflected here. So they say, okay, what's going to be the case for 25 years injection plus 25 years of monitoring? And they come to the effect of the cooling and pressure on the stresses and see if that will create some sort of a problem in terms of fracking the rocks. So the blue one is the pore pressure. You can see that the dotted lines represent the original pressure, and they are not really changing that much. You can see really there is a solid bar here. These are really huge pore volume that is not going to increase pressure, that as much as you inject, pressure increase is not going to be a concern. And this is your minimum stress, and this is your maximum stress. You can see that as we cool down the formation, the pressure in the cap rock drops, as we saw in the previous slide. So you see the solid line really dropping. And the minimal stress also drop in the cap, but significantly drop in the reservoir also. In other words, the intake formation. Because as we're cooling down, there is a huge drop in stresses here. In other words, if I'm injecting at this level, but my minimum stress is dropping down, I will be fracking the intake formation. So in other words, there is no way to inject through matrix only in this reservoir. We're gonna frac inject into this reservoir. However, since the minimum stress does not really drop below the pore pressure in the cap rock, there is no risk for hydraulic fracturing the cap rock. However, there is a second risk, that's the shear fracture. And then we go back to that similar equation of a shear failure risk. When the shear stress is greater than the shear strength, this factor is going to be 1, and then we may have that risk. And they identified that, yes, for that type of scenario, there is a risk for specific parts of the interface between the reservoir and the shale to be at that risk. The authors said in the study that they run Monte Carlo simulations on top of this, and they say that although this is possible, it looks like it's going to be low probability. However, they have their eyes on this, and they are monitoring for this type of scenario. So in a nutshell and a takeaway, answer the original questions of why, how, and when we should apply geomechanics for carbon capture and sequestration. The why is geomechanics characterization is key for the successful CCS project. How is really constraining the subsurface stress. That has to be done. Before you do any fault reactivation or cap integrity study, we have to characterize the stresses, the pore pressure, the mechanical properties before in the injection the CO2, and also the thermal effects before injection starts. That's the way we characterize. This is how we do the geomechanics characterization. And when, well, from feasibility, during the design, operation, and monitoring, geomechanics can be done, and it adds value to the project because mitigates risk, improves, and also improves efficiency. And when we look at the chart on the right here that we try to compare the cost versus the project impact, you see that geomechanics sits at the left up corner. That really is like, it's a low cost because we basically use data that is legacy data to a certain degree from wells, seismic, core, and a lot of modeling, but the impact is really high compared to other things like core, 3D seismic or 2D seismic, or even well testing legacy well data. So geomechanics is really like the best probably insurance policy that we can have for these CCS projects when it comes to mitigating the risk, improving efficiency, and then kind of getting a safety propagation across the border from regulators to communities and also the operators. So this is how we do geomechanics, and this is when and why we do it. I'll leave the audience with a few references that you can go and consult and then expand your knowledge on this topic. And if there is any burning questions after we take some here in this webinar, feel free to reach out. We're going to be my pleasure to answer and direct you to the proper answer if I don't have it. But there is plenty of material out there. And I would like to thank again SCA for the opportunity to talk to you guys about this subject. And I'm open for any question. Thank you very much.
Great, thank you. I'd like to remind the audience that you're muted, but you can ask your questions using the GoToWebinar question feature, and you will be anonymous. So we have some questions already that people have been adding. The first question is, what are the criteria to assess fault reactivation?
Very good question. So let me get a picture of a fault reactivation here. Let's go back to my cartoon. So for this, let's say this is my fault, right? This fault has a dip and a deep azimuth. And those two parameters are very important for us to define if this fault is going to be easier or more difficult to reactivate. And the game is quite simple in terms of we have the dip and the deep azimuth of the fault or strike. In other words, the orientation of the fault. But we're going to compare that orientation with the orientation and magnitude of the three principal stresses. Let's say if you have, let me see if I can draw here. I don't think so. If you have your vertical stress acting this way, the horizontal stress acting this way, and also the other horizontal stress, the in plane here. If you have your fault, let's say normal to the or aligned perpendicular to the major stress, that fault likely is going to be more difficult to slip. However, if that fault is more oriented or aligned with your maximum stress, that's going to be easier. So we're going to compare the pore pressure, and we're going to calculate the effective stresses. And with those effective stresses, we're going to compare that with the friction coefficient of the fault. And depending if the stresses are greater than the friction coefficient, we may say, well, there are zones or regions of this fault that can only tolerate X PSI. Some other regions may tolerate more. So that's really the game. Again, you have to characterize these three principal stresses, the pore pressure, and the orientation of the fault.
Thank you. What kind of tests in the field can we do to obtain essential parameters to characterize the fault stability?
Retrieving core from the fault is usually not something common, it's very difficult, but we put efforts really in characterizing the stresses, right? So we really use a lot of well data, like regular petrophysical data, like density logs for overburden stresses. And we do evaluation and review of fracturing tests in terms of a leak-off test or microfrac or mini fracs for the minimum horizontal stress. And then we do calculations to come up with the magnitude of the maximum stress. Getting the three principal stresses constraining in a good environment, in other words, with a less or little uncertainty, is really the main goal. Because with the faults, usually we're going to get a good idea of the orientation, right? So, and then even though if you cannot take pieces of the fault to the lab and measure the friction angle, there are plenty of studies out there that, depending on the type of material of the rock, we can infer how much the friction angle can go from, let's say, 0.6 to 1, and then we can run parametric analysis to really see, okay, what's the worst and best case scenario.
The next question is how to constrain the friction coefficient and cohesion of a fault.
Again, go back to the same answer here. So there are some studies published that really collected, depending on the different type of lithology, right? Let's say if you have more like a shale, sandstone, or carbonate, or sometimes even hard rocks, if you can get those from outcrops and take to the lab, you can run direct shear tests, and then you can measure this type of thing. And once you get this cloud or database of data, you can extrapolate to say, okay, I got this outcrop of the shale here, and I can really do some sort of extrapolation to X feet or meters down to the subsurface, and the friction angle is going to be bouncing between this lower and upper case here. And usually, most of the rocks, they really have friction angles that really goes between 0.6 to 1. Some may have higher, some may have lower, but it's not common. So usually, you will see that most of the geomechanical studies out there, we will start with a 0.6 friction angle, and we'll probably assume at zero cohesion to be, let's say, on the worst case scenario, because the friction is going to be really the driver for the fault stability. And if you really want to be a little bit more concerned, you say you can drop that parameter to 0.4 Or if you say, oh, my fault is a little bit more on the stronger side, more like carbonate, okay, I can go like 0.8, 1, and you really go by the like analogy of type of lithology you have for that fault that you are studying.
So we have a couple more minutes for questions. I want to remind our audience today that later today you will receive a link to a recording of today's webinar. You'll receive an evaluation form and you'll receive a link to SCA's website with more information about the consulting services we provide, including those that are provided by Everton and his team related to CO2 storage solutions, and also more information about the training course, Geomechanics Aspects of CCS Projects, which is available as an in-house course. We've got more questions. How do we evaluate the vertical transmissibility of the fault?
Very good question, and probably maybe a $1 million question, right? So there are studies that show that faults permeability can be stress dependent, right? So the more compressed the fault, the lower is going to be the aperture of the fault, and of course the permeability of the fault is going to drop, right? If you really go by that law that says that the permeability of the fault is proportional to the cubic of the aperture, right? So you can really kind of tie that back to the stress level that you can say you have at the lab, and really see do tests that can measure stress at the same time you measure the permeability, and then with that you can transfer that down to the field. It's going to be uncertainty and wrong, let's say, but at least it's going to give you some sort of a level. Let's say if your fault is sealing at the first moment, and then eventually you can kind of get a piece of rock for that same lithology, take to the lab, and let's say now I have created a fault or a fracture here in this piece of core, and then you can measure this type of stress-dependent permeability test. That can give you a good idea of how much transmissibility you may have to that fault. Of course, you're not going to be 100% accurate, but it's going to give you a good order of magnitude.
Excellent. So you've talked a lot about CO2 sequestration today. Is any of this information relevant to hydrogen storage?
The same. The physics is exactly about the same. Of course, the hydrogen is not going to be that reactive, right, when it comes to dissolution of minerals, but pressure and temperature can be applied the same way here. And this can even be extended also to the geothermal, right? So in terms of physics and mechanics of the problem, the thermal stresses, pressure, all go together. In one case is going to be more dominant pressure, in another case is going to be more dominant the temperature. But we also have to check for this type of things because they operate in a very similar way.
So a lot of fundamental science. We've got physics, we've got chemistry, we've got all the aspects of temperature. So which is it? Is geomechanics more of an engineering science or a geoscience?
Very good question. Up to this date, I don't have a firm answer for that one. So, but geomechanics is really integrated, right? Because it's mechanics applied to geological materials, right? So we really do in terms of engineering type of a stress, strain, failure, right? So the same way a civil engineer like myself, we design concrete, which is an artificial rock, right? So we create that artificial rock, and then a civil engineer goes for XPSI strength for the concrete for these skyscrapers or even the houses sometimes that we build, the bridges and things like that. That same physics that the civil engineer apply for designing a bridge can and it is applied for rocks, the subsurface. The only difference is that a civil engineer will define the strength of the concrete he needs. In rock mechanics, we cannot define the strength. We have to adapt to that one. So, and that's where geomechanics comes. We do not design the material, we adapt to the material. We check what the material can take. But it is really an integrator and a bridge between geoscience and engineering.
Thank you very much. So thanks for attending today's webinar. Later today, you will receive a link to a recording of the webinar and evaluation form and a link to the website. We have one more question that's coming in. Did you start your career in geomechanics coming from a civil engineering background?
That's correct. So In geomechanics, you will find out, depending on the school that you come from, usually you have like a three sort of professionals in this geomechanics community. Either you have a civil engineer like me, more like a geotechnical that studies soils and rocks, like rock mechanics or soil mechanics, right? Or you're going to have a structural geologist like one of my partners, and you also have a geophysicist that are not really schools that you go and say, oh, I have a degree in geomechanics as my bachelor's. There are no schools like that. Usually it's like a geotechnical civil engineer school or a structural geologist or a geophysicist. In my case, yes, I'm a civil engineer, and I started like dealing with soil mechanics first, and then I migrated to rock mechanics and got involved with the deeper and deeper rock mechanics, like in the oil and gas industry.
Very good. Well, thanks so much for your presentation today. We appreciate all the questions from the audience and look forward to receiving an email from SCA that will provide you more information about future opportunities to learn about geomechanics. Thank you. Goodbye.